Hello and welcome to our video. I'm Carlos from Plexus Lectures. This video is going to be for the QCAA 2022 Physics Paper 1. So that's going to cover both the short response as well as the first 20 MCQs. For some additional resources, feel free to hop online, check the link in the description, and head on over to our website, plexuslectures.com, and we'll have additional resources up, not just for physics, but for other sciences like chemistry and biology, ranging from videos, flashcards, and more MCQ practice questions. All right, let's jump into it. All right, so question 1. So an electromotive force we also know it as EMF, is the production of voltage across an electrical conductor due to its dynamic interaction with a magnetic field. So to me, this doesn't read as an electromotive force. So the reason for that is it describes kind of the phenomenon of electromagnetic induction, where the change in the magnetic field, so that dynamic interaction of a magnetic field induces a voltage across a conductor. All right. Option B, a difference in potential that tends to give rise to an electric current. So this to me reads as the answer for an electromotive force. Now, what we'll do is we can read through the rest and rule out the rest as well and make sense of the other choices. So the other choice is the repulsion experienced by two negatively charged particles. So again, this doesn't describe the electromotive force. This is actually describing some of the stuff you've learned before, as well as the electrostatic force, which is the force of repulsion, or it could be attraction, between charged particles. So depending on the charge, if it's a negatively charged particle versus with a positive, we have the force or the electrostatic force of attraction. Whereas if it's two of the same charge, you'd have the electrostatic force of repulsion. And then finally, let's go through D. So one of the four fundamental forces. So we can rule this out. So I'm going to list through the four fundamental forces because this is still an important thing to remember. So our four fundamental forces are going to be 1, the strong force, so strong nuclear. 2, we can have the weak nuclear force. 3, we are going to have electromagnetic force, so not electromotive, so electromagnetic. And the fourth force, which is the gravitational force. All right, and so that's going to answer question 1 for us. So one thing I like to do, and question 2 will be a good example of it, if you can't actually really pinpoint, say, B is the answer, what ones can you definitely rule out, or can they map to something else? I think option D is one of those good examples. I know the 4 fundamental forces from memory because I have to memorize that for the content or as per the curriculum. And I know, okay, electromotive force isn't one of those 4. And vice versa for A and C. Maybe B might be a bit more of a difficult one to remember the exact answer to. All right, so question 2. A photon is described as a continuous wave of light. So again, I'm going to rule this one out, a continuous wave of light. And that's because light can be described as a wave in like certain situations, so that's our wave-particle duality. But a photon is not a continuous wave, but rather one of those kind of discrete packets you would have learned in your quantum theory of just quantum. So it can be either that photon itself, so it's one of those discrete packets is a photon. All right, so B, a particle that can only propagate in a medium. I'm going to go straight off so I can rationalize why B is wrong. I know light travels through the vacuum of space. The vacuum of space is not a medium. It's the absence of a medium, essentially. So I can rule out B just from rationalizing what I know. All right, C, a quantum of all forms of electromagnetic energy. So that, to me, is going to be my answer for 2. So it reads as, okay, a quantum of all forms of electromagnetic energy, and that's one of our photons. So it's one of the quantums. All right, a particle that mediates the force between protons. So this is going to refer to a different type of particle, not a photon. This refers to something we know as a virtual particle or virtual particle photon. All right, let's continue on. So question 4, which free body diagram best represents an object being pulled at a constant speed up an inclined plane? All right, so let's go through each individual option and we'll list through what we need to know. So one of the things that I'm already looking for is an inclined plane. So here, here, here. We've got our force pulling our thing on an inclined plane has to be upwards. So our force of tension should be at the top here. So we've got it up there, up there, up there. So I can already rule out C. Some other things that we should note based on just some of the study you've done before, some of the content is you have your force of gravity, which is always pointing down towards the ground, whereas now your normal force, it's always going to be perpendicular to the surface you're sitting on. So this has been a previous question in a past paper where it was get you to define a normal force, and it's not that it's vertical to the ground, it is perpendicular to whatever surface that object is resting on. And so that's what we have for both A, B, as well as A, B, and C, and D. All right, so the next one is we need to rule out B and D. What can I think of is it's being pulled up a slope. So the first thing I'm going to check is the difference between our two forces. So the force of friction has to be less. So the force of F has to be less than F tension. Otherwise, if it's the other way around, our object is going to stay at a standstill, and that's option B. Both of these vectors are the same length, so they're the same force. So it's going to stay at a standstill. Whereas option D has your force of tension a lot less than your force of friction, so it's going to be pulling down the slope. And our object is asking for the best represents an object being pulled up a slope. So that's going to be option A. All right, question 4. An object orbiting Earth has an orbital period of 5.6 times 10 to the power of 3 seconds. What is the object's orbital radius? So this is going to be Kepler's law. So again, one of the tips I talk about in previous papers is list the variables you've been given that you know about this question. We know one of ours, it's orbiting Earth. We know the period of it, and we're trying to calculate the radius. So list what you've been given, and then see if you can find an appropriate formula in your formula book that fits within the topic that we're working in. We're working with gravity and motion here, so we know we're going to be looking in that realm of our formula book. Okay, so the formula for Kepler's law is T squared over R cubed is equal to 4 pi squared over G M. So I'm going to write on the right hand side, T is equal to 5.6 times 10 to the 3 seconds. So remember your SI units as you go through, making sure they are all correct. ME, which is going to be this mass down here, is the mass of Earth. So that is going to be in your formula book as well. So that's equal to 5.97 times 10 to the 24. And the important thing is kilograms. G is also in your formula book, the gravitational constant, so 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. All right, so another thing I've probably talked about a fair bit if you've watched our other videos is I always like to rearrange my equation before I substitute any of my values in. It takes a lot of work to carry if you substitute or simplify. But again, do what works best for you. All right, so we're trying to solve for R in this case. So we're going to go, first I'm going to move the T over to the other side. So I'm going to get R3 is equal to T squared divided by 4 pi squared, don't forget the pi squared, over GM. And that can be inversed to get you T squared GM over 4 pi squared. All right, so therefore R is equal to the cubed root of T squared GM over 4 pi squared. And when we punch that into our calculator, we get an R of 6813529.817. And our SI units, because we made sure this is in seconds, this is in kilograms, and our gravitational constant is in the correct units, is going to be in meters. So that ends up being our 6.8 times 10 to the 6 meters. So that's going to be option B. Now, an important thing to flag, I made the mistake when I was doing this question beforehand, is if you forget to punch it into your calculator and square the T, like it is here, you'll actually end up getting option A as the correct answer. So the painful thing is you can put it in your calculator, you can make a little mistake like forgetting that and get a correct option or something. The incorrect value you get on your calculator is actually one of the options in the exam, and it's been in past papers as well. So always double check, okay, have you put everything in the calculator correctly, and then move on. All right, so question 5, tau particles are classified as either bosons, leptons, mesons, or baryons. So this answer is going to be leptons. So it's been, again, a question. This has actually been a short response question in a prior paper where you've had to list the different types of leptons. So this is just going to be one of those things you need to remember. So if we want, or what we'll do is we'll just go through and list the different types of leptons. So the other leptons that you have are going to be the electron. You're also going to have the muon. So it's meant to be an M. The tau as well. So that's our answer for question 5. But then you're going to have the electron neutrino. And you're also going to have the muon neutrino and the tau neutrino. So you're going to have those 6 different types of leptons. All right, question 6. After coherent light has been passed through a double slit, the observation of an interference pattern on a screen is explained by the, wave nature of light, equal width of the slits, discrete packets of photons, distance from the slits to the screen. So this is going to be your wave nature of light. So when we think of our wave nature of light or the double slit experiment, this is one of those ones that you need to be able to explain. Again, it's a prior question on past papers, is you have a torch and it's going to explain the wave nature of light. And the way it explains the wave nature of light is as you have your double slit, I'm going to draw it quite rapidly. You have light coming up to these 2 slits, and then light will come out like this. And it will interfere. So you'll get that constructive or destructive interference. And what you're going to get on your sensor pattern or panel is going to be high intensity points of lights and low intensity points. And so that's going to be your wave nature of light, and that's how they can explain it. All right, question 7. Which change would produce the greatest increase in magnetic field inside a current carrying solenoid? So decrease the thickness of the wire. So if you decrease the thickness of the wire, it may slightly affect the mag field because density of the current can change, but I'm going to rule that one out as one of the options. Increasing the length of the solenoid. So increasing the length is not going to make a difference at all to our magnetic field. We know if we increase the number of coils, however, so this is going to lead into option C. So our magnetic field, B, is equal to U N I. We know if we increase the coils, we're going to also increase the magnetic field. So adding more turns on the wire to the solenoid, and we can already see if you increase N here, as a result, that's going to increase B. So we know C is going to be a definite answer, and let's rule out D. So using an alternating current instead of a direct current, that's going to do nothing for our magnetic field other than inducing something called a magnetic flux, because you're getting that change in magnetic field over a period of time. So we can rule out option D as well. All right, question 8. Determine the wavelength of an electromagnetic wave with an energy of 2.4 times 10 to the negative 23 joules. So we know energy can be in the form of a wavelength or be in the form of electromagnetic radiation, and that's E is equal to Planck's constant H multiplied by F, the frequency of that electromagnetic radiation. But what we're trying to do is solve for the wavelength. Nothing in this direct formula right now I can rearrange and solve for wavelength. What I know, in my formula book, you guys have probably seen it as frequency is equal to speed of light divided by lambda. But another way to look for it is your velocity. This is the exact formula that's in your formula book. Velocity is equal to frequency multiplied by your wavelength. We can rearrange this or substitute in speed of light is equal to c, which is 3 times 10 to the power of 8, is equal to frequency multiplied by wavelength. Therefore, frequency is going to be equal to your speed of light divided by wavelength. And now we can substitute that back up into our other formula. We're going to get energy is equal to hc over speed of light. We can rearrange again, and we're going to get E over h, or E over Planck's constant is equal to c over wavelength. We can continue through c over E divided by h is equal to wavelength. And then we can leave it there and substitute our values that we've given, or we can do the inverse and end up getting ch divided by E is going to be equal to our wavelength. And so if we substitute in, c is equal to 3 times 10 to the 8 multiplied by Planck's constant 6.626 times 10 to the negative 34, all over 2.4 times 10 to the negative 23. So I didn't flag it with this question, but again, always check your SI units. We're working with joules here. Energy can sometimes be given to you in electron volts, and you have to then convert it to joules to then be able to use this formula to calculate the wavelength. And so what we end up getting is 0.008283 meters, and that's going to be option C when we put it into our scientific notation. All right, so question 9. Question 9 can be a little bit of a difficult one. There's going to be an easy solution to solving this, and then there's also going to be a solution where I'm going to get you to try and remember an alternative formula for your exams. So the easy solution for question 9, let's go through it. So which diagram would result in the furthest horizontal distance traveled? So what the easiest solution I'm thinking is, I know that the optimal angle for any velocity for horizontal distance or horizontal displacement is going to be 45 degrees. So 45 degrees is always going to yield me the greatest distance. So I'm going to look, okay, 45 degrees is here for that same velocity, and 45 degrees here for D. And so I can already think, okay, B is going to be the better option over D. I can already say, okay, B's got a greater velocity than option C, 10 meters per second versus 11. So I know B is going to be more correct than D and C. Now, A, on the other hand, it's got 12 meters per second, which is a greater velocity, but it's at a lower launch angle. So if I'm rushing through the exam, this is going to be my reasoning to put B down over A. But the long-winded solution is, or it's going to be long-winded when I explain it, but I think the easiest thing to do is you need to remember a formula. Those who have done specialists would have come across this in some of your vector questions. Now that formula is going to be R, which is denoted for range, is equal to U squared, which is the initial velocity, sine 2 theta over G. So this formula, you can substitute in your U, which is going to be the 11 here, and your theta, which is the 45 degrees, G is going to be your 9.8, and you'll end up getting what the exact horizontal displacement or distance traveled will be for that projectile. So I'm going to quickly talk through how this formula is derived to make a little bit of a sense, or I guess to make some a little bit more sense of the equations using some of your linear motion equation. So let's first think of what you'd normally do if you were to do a stepwise approach, which will take a little bit longer, is your range is going to be equal to the initial x velocity multiplied by time. And you know that initial x velocity isn't going to change because there's no acceleration acting on it. So another way to state your ux as well is your ux is going to be the initial velocity, u, cos theta. So we're using SOHCAHTOA, TOA, cosine, adjacent, because we're trying to find this x velocity. So it's going to be the adjacent of the angle. Okay, another formula that you need to figure out for, so I'm going to underline it. So we've decided what the ux is equal to for our range. Our t, on the other hand, time is going to come from a different equation. So time is equal to 2u sine theta over g. So let's have a look at where we get that from. So this is going to come from, or the T is derived from one of your other kinematic equations. Vy is equal to gt plus uy. So we know when an object follows an arched trajectory, the initial velocity pointing upwards, or that vertical velocity, is going to be the same magnitude but pointing downwards. So that could be denoted with uy is equal to vy. So it's the same magnitude, but it's just pointing in the different direction. That's if the object hits the ground from the same height it's launched from. If it's launched from a higher height, like a cliff, this rule isn't going to hold true. So then we can rearrange this equation to say that, therefore, we can move that uy to the other side, and that's going to get us 2 uy is equal to gt. We can now divide that by, so it'd be 2 initial velocity over g is equal to t. What's our uy equal to? Our uy is going to be the u sine theta. So again, using our trig functions, over g is equal to t, we can now substitute. So there's how we got that formula for t. We can substitute that in, and we're going to get r is equal to u cos theta multiplied by 2u sine theta over g. So we can rearrange that again. R is equal to 2u squared cos theta sine theta over g. Now there's an identity here. So 2 cos theta sine theta is going to be equal to, so this is equal to one of our identities, which is sine 2 theta. Now, I don't expect you to remember it. This is just a stepwise to show you how this formula is derived, and hopefully it can stick with you guys a little bit. So therefore, our R is equal to u squared sine 2 theta over g. And so from that point forward, we can just substitute any of those values in, our v for 12, our initial 12 meters per second, that launch angle at 20 degrees, and our g is 9.8, and we're going to get the horizontal range. And that's a quick way to quickly go through these kind of questions where it's asking you the horizontal displacement, other than going through a stepwise progression. All right, so question 10, electric strength refers to the intensity of an electric field at a particular location. So already straight off the bat, that is going to be my answer. It's the definition for electric field, but let's go through the other options and rule them out. So change in electric potential energy between two defined points. So this is going to be related to the electric potential. So it's your change in your electric potential energy. It's telling me already there. Sum of electrically charged particles passing a point in a given time. So that's referring to your electric current. Now, D, physical property of an object experience of force in an electromagnetic field. So that's just your electric field strength, and that isn't a physical property. So that's going to be, I guess, ruled out based on this contradictory statement. Physical property of an object experiencing a force in an electromagnetic field. Electric field isn't a physical property. All right, question 11. The maximum kinetic energy of an electron ejected from a metallic surface can be increased by, using a positively ionized metal. So no, the photoelectric effect is mainly dependent on the energy of the incident photons. So if we write out our formula, the ejected energy, EK, or kinetic, or I'm just going to get rid of it, the energy itself is equal to HF minus the work function. So B, using a metal with a larger work function. If you use a metal with a larger work function, so I'm going to use green here, if you increase W, what that's going to end up doing is your HF stays constant in this case, you're just going to decrease E. So that's not going to increase the maximum energy or kinetic energy in this case. So C, increasing the intensity of the incident light. So this is partially correct. So this is going to have to get you to, I guess, draw on your understanding of intensity of light. So this would increase the net kinetic energy, but ultimately this intensity is going to increase more photons at the incident or on the incident metal, and more electrons are going to be ejected, but their EK of this, a single ejected electron, doesn't change. So essentially you're just hitting it with more light, but those individual electrons that get ejected are still going to have that same kinetic energy. All right, and option D, so we've ruled out option A, B, C, and so we're left with D. So D is going to be the answer, but let's talk through it. Decreasing the wavelength of the incident light. So let's go through our formula. E is equal to HF minus W. HF is the incident. Specifically, our frequency is going to be the incident light. We already went over it in a prior question what frequency is equal to, so I'm just going to substitute that straight in. E is equal to H multiplied frequency is equal to speed of light divided by the wavelength minus W. So our question is decreasing the wavelength of the incident light. So if I decrease the wavelength, what ends up happening is my value here is going to increase because C is going to be divided by a smaller number. So this fraction here is going to be a larger value. So that larger value multiplied through is then going to just be minused by a constant. So that's going to lead to an increase in our E. So think about some of the relationships between your numerator and your denominator in a fraction. What happens if you increase the numerator versus decrease it? And the same goes for the denominator. How does that affect my outcome for the fraction? All right, so question 12. An object experiencing uniform circular motion in a horizontal plane travels at an average speed of 8 meters per second. Calculate the radius of the object's path if it takes 0.3 seconds to complete a full rotation. So we're trying to calculate the radius of the object. So again, look through your formula book, look through what information you've been given, and then what variables you've been given in the question, and see if they match up to any of your formulas given. In some cases, you may have to substitute a variable in or derive that variable with the information given in the stem of the question. So I know I'm going to be using my velocity is equal to 2 pi r over the period. So what's our period? Our period is the time it takes to complete one rotation. So t is equal to 0.3 seconds. Our velocity for our circular motion is equal to 8 meters per second. And we don't know the radius, so we're just going to rearrange this equation. So v times t is equal to 2 pi r. Therefore, r is going to be equal to vt divided by 2 pi. I can substitute my variables in. 8 times 0.3 divided by 2 pi, and that's going to get me my answer of 0.38197. And again, think about your SI units. This is in seconds, this is in meters per second, so I know my outcome is going to be in meters. And that ends up lining up with option A. All right, question 13. A rectangular coil of 3,000 turns and dimensions of 0.1 meter by 0.2 meter is rotated in a uniform magnetic field of 2 milliteslas. Calculate the minimum number of revolutions per second required to produce an average EMF of 6 volts. So before I go any further in this question, I think this question sucks. And what we'll go through is, I guess, a long roundabout explanation for it. And from there, I think you guys can discuss and think about between yourselves whether or not you think this is a fair question. All right, so what I'm going to start off with is drawing the scenario. We have a coil of 3,000 turns. So I'm going to draw the axis that our coil is rotating. This is between our two magnets. Our magnetic field is traveling like this. I'm going to get rid of them for this example right now, but you know they're traveling. It doesn't matter if they're left to right or right to left in this scenario. And our coil is sitting, there's the axis it spins on. Our coil is sitting like this, completely parallel to the magnetic fields. And so when we're thinking of our EMF, or our equation for our EMF, we know our EMF formula is EMF is equal to the delta flux, so the change in magnetic flux over the change in time. So I'm going to start off with it in the position parallel to the magnetic fields. The reason I'm choosing parallel to the magnetic fields because I know the initial flux at that point is going to be equal to NBA cos theta, and it's at 90 degrees. So when we talk about theta, it is the angle from perpendicular to the magnetic field. So this, our magnetic fields are traveling like this again, and that dotted line is perpendicular, and that's 90 degrees when it's like this. So therefore, theta, or sorry, the magnetic flux, the initial, is equal to NBA cos 90. I'm not even going to substitute the values for N, our B, and our A because cos 90 is equal to 0. So therefore, 0 multiplied by, so that's equal to 0. So 0 multiplied by all that is going to be equal to 0. So I've got my initial magnetic flux. Now, what I'm going to do is find my final magnetic flux. And what that's going to be is I'm going to set it up so it's completely now perpendicular to the magnetic fields. So this would be at a 0 degrees. So therefore, our magnetic flux final is going to be equal to same formula, NBA cos theta. In this case, our magnetic flux final, we have N, which is 3,000. That's our 3,000 turns multiplied by B. Now this is milliteslas. Milliteslas to teslas is going to be times to the negative 3. So it's going to be times 10 to the negative 3, 0.002 multiplied by 0.1 times 0.2. That's our area here. And cos 0 is equal to 1, so it's just going to be multiplied by 1. And that gets our final magnetic flux equal to 0.12. So now let's go back to our EMF equation here and figure some stuff out. So our EMF, our magnetic or our induced EMF should be 6 volts. So 6 volts is going to be equal to the change in magnetic flux, your final minus your initial. Our initial is 0, so we're going to be left with 0.12 over our change in time. We don't know the change in time, but we can rearrange this equation to find out the change in time, which is just going to be 0.12 divided by 6, which ends up being change in time equal to 0.02 seconds. So again, making sure my SI units, we converted back up here our milliteslas to teslas to substitute into our mag flux equation. So we have 0.02 seconds. This isn't going to get us our answer. We've got 1, 3, 13, or 15 revolutions per second. But what we do know, from the scenario that I've drawn, it takes from here to here to complete a quarter rotation. It takes 0.02 seconds. So let's stepwise through it. So if it takes 0.02 seconds, it's going to take 4 times that to complete one total revolution. So it's going to take 0.08 seconds to complete one revolution. And so from there, I'm going to do 1 second divided by my 0.08, and that's going to get me 12.5. So I can do 12.5 revolutions in 1 second. The only option that's close to 12.5 is going to be option C, so 13 is going to be my answer. All right, so question 14, which Feynman diagram correctly depicts neutron decay? So again, this is one of those ones you're given to memorize. So important things that you need to know. Looking at these kind of Feynman diagrams is that we need to know that a neutron, so I'll write it out, a neutron is an up and 2 downs. And a proton is going to be an up, a down, an up, or an up, up, down. So let's go through and make sure we've got that. So A we can rule out because it doesn't have, well, it's got our proton here, but it doesn't go to, it's got our neutron here, but it doesn't go to a proton. It goes to another neutron. So that is not neutron decay. Option B has it. So option B is correct with our neutron going to proton. Same with option C. And the same goes for option D. So let's go through and figure out option D doesn't. It's got an up, down, down. So we can rule out option D as well. Fantastic. So we're only left with option B and option C. So what are the only two differences? Is that one has a W positive or W positive boson and a W negative. An important thing is our neutron decay has a W negative. So that is going to be option C is the correct option. So the two things to remember for this type of Feynman diagram for your neutron decays is knowing if you're to put your neutrons and protons as quarks, that you know a neutron is an up, down, down, and a proton is two ups and a down. All right, so question 15. An object's velocity can only be measured relative to a fixed reference frame, B, the speed of light, C, an object at rest, or D, an observer. So the answer here is going to be to an observer. An object at rest isn't going to get us is going to get you a velocity, but it's not going to get you the true velocity. So the speed of light, that is going to get you a velocity relative to that point of frame or frame of reference, because we know the only constant within each frame of reference is going to be the speed of light. And the same goes for A. So we know option D here is the correct choice. So question 16, two vectors are shown, vector x and vector y. Which option represents the resultant vector x plus y? So let's go through and draw our two vectors. So we're drawing x plus y, so we're doing it head to tail. So x is here. I'm going to draw the horizontal in at 40 degrees here, and it is 35. And then we are adding vector y, which goes down like this, and it goes down from the horizontal, this new horizontal, goes down at 60 degrees here, and it has a magnitude of 48. And so we have a new vector from the tail to head. A resultant vector is down in that direction. So it's going to be, so I guess already looking at our options, we can rule out B because B is pointing upwards from horizontal, and same with C. C is pointing upwards from horizontal. And we know our new resultant vector is going to be pointing down from horizontal. And so there's two options we can go through. We can think, okay, let's have a look what's different between our options. So option A and option D. Option D is, okay, both the magnitude is different as well as the angle, and same for option A. So you can either try and figure out, okay, what's the angle or what's going to be the magnitude of that resultant vector. And so for me to figure out that magnitude is, well, I'm going to do the solution figuring out the magnitude of the resultant vector. So this length here, so that length is going to be equal to a triangle essentially. So it's going to be the positive y. So if I think about it is, we're going to use Pythag. So I'm just going to say, let's call this vector w. So vector w's magnitude is going to be equal to the x component of vector x plus the x component of vector y squared, so using Pythag, plus the y of x plus the y of y squared as well. So let's think. So x of x is going to be equal to 26.8. How do I get that? So again, I'm using my trick. So I'm trying to find out this value here, the x of x from there to there. So when I think of my trig, I pull out SOC, katoa, and I'm going to be using cosine because I'm going to do the adjacent. So it's going to be, to get x of x, that's going to be equal to 35 multiplied by cosine theta. To get the y, it's going to be 35 multiplied by sine theta, and our theta in this case is 40. And we're just going to do the same here for vector y, but our angle is going to be 60. And so a thing to remember is we're going to still have a positive x. I'm happy with it being a positive x, but the thing that we have here is it's going to be a negative y. So I know, so xy is equal to 22.5, and again, that is 35 multiplied by sine 40. Our y, x, is going to be equal to 48 multiplied by cosine 60, which we end up getting 24. And our y of y is going to be equal to negative 41.6. So when you punch it into your calculator, you'll be punching in 48 sine 60, and you're going to get a positive 41.6. But you need to remember, relative to this diagram, our y is pointing in the negative direction. And when we substitute that all in, we end up getting the magnitude of vector w equal to 54. And so that's not option A, and we've already ruled out option B and option C because they're pointing in the positive direction, or their angle is positive from the horizontal. So we are left with option D because it has that 54.3. Okay, so question 17. An object is in orbit 400 kilometers above the surface of the Earth. The Earth has a radius of 6.4 times 10 to the 6 meters. What is the magnitude of the gravitational field strength experienced by this object? So again, look through your formula book. Let's have a list of our variables. So we're given the radius of the Earth, and we're also given how far the object is orbiting above Earth. So our total radius, one of our variables, is going to be 6.4 times 10 to the 6 meters. So that's horribly written out. I'm going to do it better. 6.4 times 10 to the 6 meters plus, and this is going to be 400 times 10 to the 3 because we're converting kilometers to meters. And so that's our radius. Other information we need to know is going to be our mass of our planet as well as the gravitational constant. And the reason for that is we're trying to determine G, or the gravitational field strength, at a particular point. And so the formula from the formula book we end up using is going to be G m over r squared. So we've got our r squared value. What's G? G is our gravitational constant. That is 6.67 times 10 to the negative 11. And our mass of Earth is equal to 5.97 times 10 to the 24. So we end up getting G is equal to 6.67 times 10 to the negative 11 multiplied by the mass of Earth, 5.97 times 10 to the 24, all divided by our radius squared, which is that 6.4 times 10 to the 6, plus our 400 times 10 to the 3. And that is squared, so don't forget to square it, and you end up getting a G equal to 8.61157, and that will continue on, but our question only wants it to 2 sig figs, and it ends up being 8.6 times 10 to the times 10 to the 0 meters per second squared. Fantastic. All right, question 18. The primary and secondary coils from a lossless transformer are shown. Compared to the primary coil, the secondary coil will experience decreased A, power, current, voltage, or resistance. So our option here, or our correct answer, is going to be, it's going to be a decreased current. But let's rationalize through this. So you're given multiple formulas in your formula book. One of them is Vp over Vs is equal to Np over Ns. So let's rule out our voltage, and from here we can neglect resistance because resistance isn't going to change between these. It's a lossless, as well as our power. We don't need to worry about our power in this case. So I want us to rule out voltage and then rule in current and see why current is a true statement. So our Vp over Np. So if we increase, or in our case, what we've done is increase the number of coils on our secondary. And so if we increase the number of coils on our secondary, for this ratio of Np, primary coils to secondary coils, for it to be true, we must increase the ratio, or increase the voltage in our secondary coil, and that would be the resultant. So compared to the primary coil, the secondary coil will experience a decreased voltage? No, we know it's going to experience an increased. The other equation we're given is Ip Vp is equal to ISVS. So right now it's not too useful for us, but it's going to help us with our current. So I'm going to rearrange this equation as Vp is equal to ISVS divided by Ip, and therefore I'm going to move that Vs to the other side. Vp is equal to Vs, which is now equal to Is over Ip for our primary. So one thing I'm going to highlight now is we can substitute our equations together. So that Vp over Vs maps up with this. So we're left with now a statement of Vp over Vs is equal to our Np over Ns, which is also equal to our Is over Ip. So let's again think about our ratios or our fractions and what happens when you change a numerator versus a denominator. So if I increase the number of coils, which this option has, secondary has more coils than the primary. So if I increase the number of coils in our secondary, we must either increase for these two to remain equal, you must either increase the current in the primary, or you can decrease the current. So sorry, I just erased the I, or decrease the current in the secondary. So that's how option B is going to be correct. So think about it. If you increase the denominator of a fraction, the outcome of that value decreases. So in our case, we've increased the denominator, and so our outcome is going to decrease. And so we're not changing the current of our primary, but as a result, it's going to decrease the current of our secondary, which will keep the ratios equal to one another. All right, cool. We're on to the final page. So question 19, a current carrying wire is placed perpendicular to two magnets. As the current in the wire is changed, the force acting on it is recorded. So the question is, the gradient of the line of best fit is proportional to the potential difference, electromotive force, resistance of the wire, magnetic field strength. So let's have a look at our relationship between our graphs. So it's a linear model, or it's a linear function. So y is equal to mx. I'm not going to do a plus c because our c would be 0 because it intercepts at 0, 0. So let's add our variables. Y is equal to the force times 10 to the negative 5. That's not going to make much of a difference right now for us, but in short response questions, it's an important thing to flag. When your y variable, or any of your variables, your x or y, has units to it, but it also has a unit to a power of, so like 10 to the negative 5. So that will make a difference in your calculations. It is equal to m multiplied by x, so m is our gradient multiplied by our current, which we know in formulas is represented by I. So what I'm going to do is I'm going to look in my formula book and see if there's anything that maps out similar to that equation in, or this situation as well, in my formula book. So what I end up finding is force is equal to B I L sine theta. So what are our similar things? It's equal to F, and I is one of our variables. In this case, length and sine theta is not going to make a difference, or we know sine theta, it's placed perpendicular to the two magnets. So that's going to be sine 90, which is 1, so we know that we can rule out. And the length isn't changing either, so the length is going to be also part of our gradient. So we can think force is equal to BL, so I'm going to group that there so we can map it to our I, multiplied by I. So in this case, we don't have length as one of the options for the gradient, but we do have B, which is our magnetic field, which is option D. All right, final question for the MCQs, and then we can go on to the short response. So which option lists the gauge bosons in ascending order of the strength of force they mediate? So let's think of the strength of forces first in weakest to strongest. So my weakest force, I'm going to start at a weak nuclear force, goes to an electromagnetic force, and then a strong nuclear force. So what has I'm going to just put it with a W, weak nuclear force is a Z boson. What has our electromagnetic force? That is a photon, so that is electromagnetic force. And finally, what has our strong force is a gluon. So that is going to be our answer there, is option D is the correct answer. And that's going to complete our MCQ, and I'll get the short response started. All right, now, so we're on the short response. So this is still paper 1 for the 2022 paper, but now we're starting on the short response question. So question 21, a hot iron bar was observed to have a deep red color as the iron bar was heated further. The color changed to orange. Explain the observed color change in terms of black body radiation. So for this question, let's break it down into 2 steps. I want to describe the scenario in terms of black body radiation, and then I'm going to use Wien's law to explain the color change. So first thing I'm thinking is I'm not going to type out the exact answer. That would be ideal. So feel free to jump onto the QCAA's website. They'll have the typed out exemplar answer. I'm just going to put down some tips to help you answer this question. So the first step is describe what's happened in terms of black body radiation. So heating the iron bar first is what represents. So heating the iron bar represents represents black body radiation. And what we also know is that where spectrum of radiation or emitted is due to the conversion of thermal energy. So our thermal energy that's created can then be converted to a spectrum, which is going to be that visible light. So I'm not going to bother writing that point down. I'm just going to leave it there for you guys to take in. So point 2 is now using Wien's law to explain the color change. So Wien's law is your max, so this is for black body radiation, wavelength max is equal to B, which is a constant over the temperature. So what we know is if you increase the temperature, or let's think about, so we've done it in the plenty of those MCQs, is thinking about the relationship between a fraction. If you increase the temperature, which is on the bottom of our fraction, the denominator, what ends up happening is you decrease the wavelength. So that's what I would write happening here. So as you increase the temperature, you decrease the wavelength. What proves that? Well, red itself, red as a color, is at approximately 700 nanometers is the wavelength. Whereas it transforms, so it goes from red to orange. And orange as a wavelength is approximately 590 to 620 nanometers. So what we have here is an observed proof of black body radiation, because we know as temperature increases, your wavelength max, or the visible wavelength, will decrease. So as an outcome, we started off at a higher wavelength of 700 nanometers, but as the temperature increased, we went to a lower wavelength of 590 to 620, which is that orange, that color change from red to orange. All right, so question 22, a collection of mesons was observed by a detector to move an average distance of 11 meters when traveling at 95% of the speed of light. However, based on their properties, the mesons were expected to travel an average distance of 3.4. Explain the difference between the observed and expected average distances. So to explain this is we're going to use our quantum theory. So we know when something is traveling really close to the speed of light. In our case, it's 0.95 c, or 95% of the speed of light, which is c, which is 8 times 10 to the power of 8. Speed, so when you're traveling at 0.95 c speed, that means ultimately the mesons are going to experience time dilation. And that's time dilation relative to a stationary observer. So I would add those points in there. If you want to see the full explanation that we've put up as well, check the link in the description. We've got our own annotated examples for these questions, as well as, again, hop onto the QCAA website and they've got their own annotated examples as well. So the other thing is, this means that the mesons appear to travel for a longer distance, for a longer period of time, and in their frame of reference. And if they're traveling for a longer period of time, that means they're going to travel for a longer distance. So I'm not going to bother again writing out that point. It's a bit wordy. I want to get through these questions a little bit quickly, so feel free to click the link in the description. But what I want to do is actually show you with some math. I want to show some working about how we can prove this. So the first thing that we know is our mesons are supposed to travel 3.4 meters, right? And they are traveling at 0.95, so this 0.95 c. So I'm going to do that 3.4 meters divided by this time, or sorry, the speed that they're traveling at, and that should give me the time, or how long they should live for. So I'm going to do it divided by 0.95 times 3 times 10 to the 8. And that gets me a 1.2 times 10 to the negative 8 seconds. So that's how long a meson should live for. And so if that's in their frame of reference or in their inertial frame, we can use our time dilation question or formula. T is equal to T naught over the square root, divided by the square root of 1 minus V squared over C squared. V in this case is going to be 0.95 C, and we can cancel them out. So we end up getting a formula of 1.2 times 10 to the negative 8 divided by the square root of 1 minus 0.95 squared. That ends up getting me 3.8 times 10 to the negative 8 seconds. So from the observer's perspective, they actually travel for 3.8 times 10 to the negative 8 seconds. So that's the time dilation. And what we end up finding out from that is if they live, or from the stationary observer's perspective, if they live for 3.8 times 10 to the negative 8 seconds, and they travel at, times that by 0.95, the speed they're traveling at, 3 times 10 to the 8, we end up finding out that they actually travel for about 10.89 meters from the observer's point of view. And so the other thing you can do is you can also look at length contraction and prove with length contraction that it goes from 11 meters down to 3.4 from the perspective of if you were the meson traveling at that speed. But this is another good example to think about, okay, your quantum theory and your time dilation. So what you're trying to do when answering this question is thinking about time dilation and relating it to the situation. When you travel really fast, you'll experience time dilation, or the observer will have time dilated for them in comparison to the particle or the thing moving at that speed. And if it's time dilated, they're going to still be traveling at that same speed, but it will be traveling at a longer period, so the total distance will be longer. Okay, so question 23. The diagram shows the electron energy levels for hydrogen. Calculate the energy released in joules when an electron moves from the third to the first energy level. All right, so this is going to be a very common kind of problem that's asked actually a fair bit on multiple papers when you're thinking about your energy or energy release from electrons jumping from one shell to another shell. So this is going to be a multiple part question. So looking at part A, calculate the energy released going from the third to the first energy level, or otherwise known as, when we think of our first energy level, we always call it, or otherwise it's known as the ground level. So our energy, or delta energy, is what we're trying to calculate, has a formula. It's equal to the energy of the final state minus the energy of the initial. So our initial is at N3, based on from the third to the first. So that's going to be a negative 1.5 electron volts, and N1, our ground state, is negative 13.60 electron volts. So our delta E is going to be equal to negative 13.60 EVs. So this is going to be an important thing. So sometimes these things can be measured in joules, or in the case of a lot of our electron energy or electron energy level problems, they use electron volts because it's a lot neater to write that than have times 10 to the negative 19 joules, for example. And so that is minus, and I'll put in brackets here because it's minus a negative 1.51 EVs. So that's our initial. We end up then getting a delta E equal to negative 12.09 EV. So that is what's released. There's a negative 12.09 EV released. And what we need to do is convert our electron volts to joules. So there is not a formula, but it tells us in our formula book that 1 electron volt is equal to 1.60 times 10 to the negative 19 joules. So whatever we get in electron volts, we're going to multiply it by 1.60 times 10 to the negative 19. And that's going to end up getting us, so I'll write in a different color here, we're going to do that answer in our electron volts times 1.60 0 times 10 to the negative 19. That ends up getting us 1.93 times 10 to the negative 18 joules. So our answer here in the box that we're going to put down below is just going to be 1.93, that's 3 significant figures like in the answer, times 10 to the negative 18. All right, let's continue. All right, so part B is, let's have a look at what we've been given. The visible light emission spectrum for hydrogen is shown. So we've been given a emission spectrum here, and explain why hydrogen only has 4 emission spectrum lines in the visible spectrum. So they've already given us what the visible spectrum is, 400 to 700 nanometers. So we're thinking about like that purple to a red here essentially. So let's go through. We need to explain why there's only 4 emission spectra lines in the visible spectrum. So you'll see probably different ways to explain this question. I'm going to try and take a little bit more of a slower approach and a more logical approach to think about it. So the first point that I want to get down is as you change, as we saw in the previous part A, as you change in orbital level, you will end up you will release energy. And what we know when you release energy, oh, I can't spell. When you release energy, you can then produce a wavelength of light. So released energy goes to a wavelength. And I'm not going to say light, I'm going to say more or less electromagnetic radiation. Wavelength of, I'll write light here, but I've said electro just to save me some writing time. So we know that because we have our formula. E is equal to hf, or otherwise we know frequency is equal to the speed of light over the wavelength, hc over our wavelength. So what we can do is just an added step. This isn't going to be necessary for the problem, but if we were to determine or work backwards, we could say the wavelength of light that can be predicted by the energy released would just be wavelength is equal to hc divided by E. So all I've done here is just rearrange this equation. And if we knew what the energy is, oh, didn't mean to erase it. If we know the energy that's released, and remember, not in electron volts, this equation will only work for joules. So if we go back to here, we will get the energy release in electron volts, but like what we did here, we'd need to convert it to joules, and then we'd be able to find out the visible light spectra. But what I'm going to do is I'm going to take a different approach, and I'm going to figure out how much energy we have to release to produce those different wavelengths. So essentially what I'm doing is I'll draw it on this spectrum. I want to know, say 400, a wavelength of 400 nanometers is here. I want to know what energy they need to have. And say for 700 up here, I want to know what energy needs to be released from your electrons jumping shells. So my first step is going to be figuring out, okay, the visible light spectra. So at 400 nanometers, I'm going to use, I'll highlight it in blue, this equation here. I'm using E, especially the hc over our wavelength. And remember, this is in nanometers, so I need to convert that to meters. So nanometers to meters, I need to do it by times 10 to the negative 9. So my formula will be energy is equal to, H is Planck's constant, 6.626 times 10 to the negative 34, multiplied by our speed of light, which is 3 times 10 to the 8, all over our wavelength, which is 400 nanometers, but I'm converting that nanometers to meters for our SI unit, so I times it by negative 9, and then punching that in my calculator, I end up getting 4.97 times 10, and my units here is joules. So I need to convert that joules to electron volts. So in our previous examples, to go from electron volts to joules, we multiplied it here. We multiplied it by our 1.6, but if we want to go backwards, we're going to have to divide it by 1.6 times 10 to the negative 19. So I'll write here in blue, divide by 1.6 times 10 to the negative 19. We're going to end up getting an EV is 3.12 EV. And we're going to do the same for at 700 nanometers. So the only thing we're changing in this E equation is E is our denominator here for our wavelength. So it's just going to be the same. Planck's constant, 6.626 times 10 to the negative 34, multiplied by our fraction, which is the speed of light on top, 3 times 10 to the 8, divided by 700 times 10 to the negative 9. Again, we're converting our nanometers to meters. We end up getting a 2.84 times 10 to the negative 19 joules. Again, we're going to divide that by our 1.6 times 10 to the negative 19 to convert it to electron volts. And we end up getting approximately 1.77 EVs. So we know for visible light to be produced, the energy levels, or the energy that has to be released, has to be anywhere between here, 3.12 EVs, to the top level here, which is 1.77 EVs. So then what we need to do is we can go back to our energy levels here and have a look for proof of what energy levels resultantly give us that released energy. So I'm going to look through, and I believe our answer should be the energy levels between 2 and 4. So if I was to jump from level 4 to level 3, I'm going to release about 0.7ish. That's not going to be within my range, but maybe level 4 to level 2, I'm going to release about, looks like 1.6, and if I scroll down, it's maybe just enough to fit within that range. So that's how we're working through this problem here. Is I've put down my range in EVs, and we can see we've got a point here, point here, point here, point here. Another way to go through this problem would be using this equation and figuring out what each individual one corresponds to. But I like figuring out the range from 3.12 electron volts to 1.77 electron volts, and then I can just look at the energy levels here. I can make my decision. All right, so question 24, a rectangular loop is placed in a uniform magnetic field, like what we see in this situation. Calculate the change in flux through the loop when it is rotated 60 degrees around the vertical axis. Show your working. All right, so this is going to be our vertical axis, or our rotational axis is what I'm going to think. And it looks like it's going to be rotating clockwise. So to make a little bit more sense of this problem is I'm going to redraw and from a different perspective so we can get a better understanding and start thinking about applying some of our formulas. So we have our north, and we also have our south over here. In the blue, I'm going to quickly draw in our magnetic field lines going from north to south. So initially, so stage 1, and I'm going to put my axis of rotation here. Our, I guess, let's call it our loop, is sitting completely parallel to the field lines. But in stage 2, it's still going to be north, it's still going to be south. We still have our magnetic field lines traveling across, but then we rotate 60 degrees clockwise, because I'm just going based off of this here. It rotates around that axis, and that's my axis that I have here. I'll highlight it, try highlight it in the orange or even a yellow. Hopefully it stands out a little bit more. That's our rotational axis, this point here through the coil or through the loop. So we've rotated from horizontal, or from parallel to the magnetic field lines is another way to think of it, 60 degrees. So what we're going to use for our formula, so we're trying to calculate the magnetic flux running through. Our magnetic flux formula is going to be flux is equal to BA cos theta. So we know what B is equal to. we also know what A is equal to. We can calculate that. So I'm going to put B as, so it's 5 milliteslas. To convert milliteslas to teslas, we're going to times it by 10 to the negative 3. So 5 times 10 to the negative 3. Our area, again, we need to convert it to meters, is 20 centimeters by 30 centimeters, or 0.2 times 0.3. Now, the hard thing to remember or think about is, what is our theta? What is our angle? Is it 60 degrees? So if we're using cos, it's not 60 degrees, because remember, for your magnetic flux, we need to measure the angle from perpendicular to the magnetic field lines. So this one here is our perpendicular to the magnetic field lines. It makes a right angle with the magnetic field lines. So 60 or 90 degrees is what this total is made up of. So 90 minus 60 is going to be 30 degrees here. You could use sine 90 because you're rearranging, or sorry, sine 60, but let's stick to using the cos theta formula, which is the one you're given in your formula book. So from there, we end up getting mag flux is equal to 2.6 times 10 to the negative 4 WB. And so our answer is going to be 2.6 times 10 to the negative 4. So an important thing with this one is flag that you have the units converted to your proper SI units when calculating this formula. Another tip is, I always find it super necessary to draw out these magnetic field problems, because having a different perspective can help you understand it. Especially that question 13 in the 2020, this paper, is a little bit difficult to understand if you don't draw it out. I definitely had to draw that one out to first understand or figure out a way to solve that problem. Okay, so question 25, describe how electromagnetic radiation is propagated by the interaction between electric and magnetic fields. So we've got a pretty easy or straightforward explanation or describing kind of question. We don't need to do any formula work. So this is where having a good understanding or a good memory of the theory of all the content comes into play. So I definitely recommend hopping onto our website and having a use of some of our flashcards, because we use some of these questions or use some of the curriculum syllabus, or I guess, yeah, syllabus checkpoints to base our flashcards around, because they're the things that you can be asked, especially describing how electromagnetic radiation is propagated. So in this case, an oscillating charged particle can induce a magnetic field is going to be our first point. So oscillating charged particle, so will induce a mag field. And the other thing is, if we have a changing mag field, so changing mag field, what we can then do is induce an electric field. But one thing has to be, so I should put field here. So if you have a changing mag field or changing magnetic flux, you can then induce an electric field. But that electric field has to be, this is very specific and very important, same with that previous question, it is at a perpendicular to the mag field. At perpendicular to the mag field. And so that's going to be our answer for question 25. All right, question 26, single mark. So hopefully this one's an easy one. You've got carbon-14 undergoes nuclear decay to nitrogen-14. List two types of particles whose total number must be conserved in this reaction. So this is a listing question, and that's all you need to do is list the particles. You don't need to explain anything that's going on. So this is one of the topics you would have learnt near the end of the year under your standard model kind of stuff, and that is the conservation of lepton number and baryon number. So your answer here is just going to be baryons as well as leptons. So it's maybe a handy thing to know, not a necessary thing to know. You can, in the curriculum, you're not required to know how to do the baryon or lepton calculations. It's not an accessible or an examinable thing. All you need to know is that there is the conservation of lepton number and baryon number. Okay, so question 27. Object A is 5 times the mass of object B. So this is going to be an important thing to remember. The graph shows the contribution of each object towards the strength of the net gravitational field between them. All right, determine the total distance between the center of the two objects. Show your working. So I'm going to take a stepwise approach again with this problem. First, let's discuss and have a look at what's going on in the graph, because there's 2 lines and I want us to break it down and understand what's happening. So with our dashed line, what we notice is we have our x-axis, distance from the center of planet A. So when you're really close to planet A, that gravitational field strength is really high from planet A. And as you get further and further away, so moving towards the right on the x-axis, it starts getting weaker and weaker and weaker. And we have a point here where these 2 gravitational fields intersect. Another thing we have is this solid line for planet B. And so the way I interpret this is down here, when the distance from the center of A is really small, so you're still really close to planet A, but you're actually really far away from planet B. So I will draw the situation down here with our 2 planets. So here is planet A and planet B. And so what we end up having is a distance which is going to be x, which is what we're trying to calculate. But when our x-axis of our graph is, I guess, radius of A. So if you're really, really close to radius of A, so it's to the point it's like just above 1 here, you're going to be very close to planet A, but you're also going to be very far away from planet B. So the gravitational field from planet B is actually going to be really, really small. But as you get further away from planet A, so I'm going to use this yellow color, as you get further away, moving, you get closer and closer to planet B, and that planet B gravitational field starts increasing. So this is what's happening with our graph. This is an important concept to have down, is being able to break down a piece of information like your graph. And let's have a quick look. Our units, we have distance from A is 10 to the 7 meters. And our gravitational field strength is meters per second. No units here, or no like multiplication factor that we need to think about. So we need to figure out the total distance between the center of these 2 objects. So we're trying to figure out, I'm going to get rid of this lines now, other than the gray. We're trying to figure out x, the distance between these 2. But we have no idea what x is equal to. So what we do know is x is going to be equal to RA, whatever RA is, plus RB. So we can think of it in terms of, if we know what RA is, we can also try and figure out what RB is. If we know what X is, we can figure out the other 2. But now let's think about how can we calculate this. And so what we're going to do is we're going to use the interception point here. That's going to be a very crucial point for our working out or through our problem solving. So what is that interception point? That interception point tells us that the gravity due to planet A, and I'm going to use magnitude because they're going to be working in opposite directions, right? The gravity of planet A is going to be pulling towards planet A, whilst the gravity of B is going to be pointing towards B. Gravity is a vector or a vector measurement, so it has a direction. So I'm using the magnitude to get rid of that vector. So it removes it if it's a positive or a negative. So gravity of B, so at that point where I guess our distance is approximately, say 35 here, 35 times 10 to the 7 meters away. So I'm going to continue writing through. So let's put our formula in for gravity. So gravity due to planet A is going to be equal to G, planet A's mass, ma, divided by RA, the distance away from RA. Whereas gravity due to B is going to be G, gravitational constant, mass of planet B, divided by the radius from B. So let's list through, or first let's actually simplify before we actually throw in some variables. So we can cancel out G, because if you divide by G on one side, it will cancel out G on the other side. So we're left with, and I believe I've forgotten something fairly important with our formulas here, it should be R squared. So RB squared, RA squared as our denominator. So we're left with now the statement MA divided by RA squared is equal to MB divided by RB. So what we want to do here is get everything in terms of a certain variable. So we know what RA is when they're both equal to one another. RA is going to be equal to 35 times 10 to the 7. So I'm going to neglect the 10 to the 7 here because I can add it on later or afterwards. Now RB on the other hand, we can rearrange this above formula for RB. So RB is going to be equal to X minus RA. But what's our RA equal to here? 35 times 10 to the 7. So that is going to be equal to minus 35 times 10 to the 7. So we've got our RA and we've got our RB though, but we don't have our MA, nor do we have our MB. So let's go back and have a look at our situation. So object A is going to be 5 times the mass of object B. So I'm going to say MB is equal to M. We've said MA is going to be equal to 4 times MB, which is the same as saying 4 times our little m. Or sorry, it's 5. So now we can substitute those values in. So it's 5m divided by 35 squared. So I'm just going to drop the times 10 to the 7 here, is equal to m divided by, here it is, x minus 35 all squared, because it's RB squared. What we do notice here is we can cancel out the m's between the two, so I'm going to continue over the page, leave it at the top there, and I'll use red so it can stand out for us. So we're now left with 5 divided by 35 is equal to, so I'll put the therefore, 1 over x minus 35 squared. So the next step to rearrange is we can just inverse both sides, and we're left with, and I'm missing the square on the 35, we get 35 squared divided by 5 is equal to x minus 35 squared, because that's divided by 1 because we inversed it. Now we're left with, I want to move the square root. So to do that, I'm going to be left with the square root of 35 squared over 5 is equal to x minus 35. You can simplify this if you want. That would be simplified to the square root of 35 over, or it would be simplified to, 35 over root 5. To me, it doesn't really matter because we're going to get to a point where we can just punch this all into the calculator, and I don't want to make any simplifications, mishaps, or mistakes. So that's going to be equal to the root of 35 squared over 5 plus our 35 is equal to x. Then we can punch that into our calculator. We get an x value equal to 50.65. Now the important thing is, remember, it's 50.65 times 10 to the 7 meters. So when we round to two significant figures, that is just going to be 51 times 10 to the 7. And so that's going to be our question done there for question 27. All right, we're finally here. We're up to question 28, the final question for the paper 1. And so let's go through it. Hopefully it's an easy one. So an object of mass 200 grams moves in a uniform circular path with a radius of 25 centimeters. The time taken for 10 revolutions is 3 seconds. So A, calculate the distance traveled by the object after 3.9 seconds. Show your working. All right, let's take again a stepwise approach. I'm thinking I've said it too many times already. So 1 revolution. Let's first figure out what 1 revolution is equal to in distance, because we were trying to calculate the distance here. So let's first figure out what 1 revolution is equal to. So 1 revolution distance, and let's have it in meters. Our SI unit is just going to be what's the formula for the circumference of a circle? 2 pi r. And so that's going to be equal to 2 pi multiplied by 0.25. Where am I getting the 0.25? Up there from our 25 centimeters, converting it to meters. Now, what do we end up getting? That is equal to 1.5708 meters. So that's the circumference. So when you complete one revolution, that is the circumference. I'm going to take a ratio approach to solving the distance. So I know if you go for 3 seconds, you will cover a distance of one revolution. You'll cover a distance of 10 revolutions, because that's up here, 10 revolutions in 3 seconds. So 3 seconds will get you 10 revolutions. If you go for 3.9 seconds, I want to know how many revolutions you do. To get from 3 to 3.9, what you do is you're timesing it by 1.3. So what you do to one side, you do to the other, times by 1.3. I get 13 revolutions. I know that one revolution is equal to 1.5708 meters. So I'm going to times that by the 1.5708 meters. That ends up getting me 20.42 meters. So my answer to two significant figures is just going to be 20. So I'll change color, 20 meters. All right, final part, part B, calculate the centripetal force acting on the object, show you're working. So we need a formula for our centripetal force. It's our circular, or it's going to be in our motion equation. So that is going to be F net is the one we're looking for. Again, think about the variables you've been given in the question. F net is equal to mass times velocity squared over r. Let's list our variables that we've been given. Our mass is equal to 0.2 kg. We're using our SI units. In the question, they had given us 200 grams. Let's convert it to kilos. We've also been given our radius, again 0.25 meters. And what we're trying to do here is we're trying to figure out what V is equal to. So we've got to then have a look, what's our formula for V in our circular motion formulas? V is equal to 2 pi r t. So that's how we can calculate out our V. So what is T in this case? T is our period. So it's the time for one complete revolution. So T is equal to time for one revolution. So if it takes us 3 seconds to complete 10 revolutions, I'm going to do 3 divided by 10, and that gets me 0.3 is my period. So I can get velocity is equal to 2 pi times 0.25 divided by 0.3, which is then equal to, V is equal to 5.24 units is meters per second. Then we can substitute this value now. We have our velocity into our F net equation. Our F net equation is F net is equal to 0.2 multiplied by 5.24 squared all over our radius, which is 0.25. When we punch that into our calculator, we get 21.966 newtons. 2 sig figs is 22 newtons. And that's it. That's the end of paper 1 for the 2022 physics paper. So definitely hop online, have a look at Plexus Lectures. We've got some great materials there for you guys to use, and hopefully it will make a difference, especially the flashcards for memorizing some of those content or those questions where you've got to pull from your memory and remember either a list of items or some theory. All right, thanks for watching.